we're going to be talking about chain rule, what chain rule is, and how do we use chain rule, and why it's important. So, first off, I just want to clarify that chain rule is a formula. Right here, as you see, this is the formula of chain rule, and this is branched out of a derivative. Now, before we get into everything, I want you to think of a banana. So, many people have different preferences, right? Many people, when you cut them, you essentially want to make it a certain shape. Some people like dice, some people like circles, some people like really diced. It all matters on preference. And with every new way to cut the banana, there's essentially a different formula for each. And the banana is essentially your rate of change in this case. What I'm trying to say is that this chain rule is just one of the very many formulas attached to how to find the rate of change of a function, which is essentially the derivative. Now, I'm not going to go too much into derivatives today, but essentially a derivative is a way to measure how fast your position changes over time in a function. We learned that in chapter 1 that for limits we followed this long formula to get the instantaneous slope, which is essentially our rate of change at a given moment. Well, the derivative is the same thing. It's way more simpler. And using thinking about the derivative as a banana and knowing how all functions are different in their own way, like there's exponential functions, there's square root functions. All of them have different formulas in how to get the rate of change of each. And today we're going to look at what functions use the chain rule. On the side right here, I have two great examples of when we need to use the chain rule. And I want to just give a few contexts about the chain rule. The reason why it's even called the chain rule is because what happens is that the chain rule is a variation of the power rule as well as just normal logic. We know the rainbow method, we know the chain method. When we distribute functions like magnitudes, we know that we have to distribute it kind of like a chain. The chain rule is kind of like that in the sense that you have to distribute the numbers, but instead we have to find the derivative of each. It's kind of like a chain in the sense that it keeps following and following. For example, right here, this example right here, the reason why we even need to use chain rule for this is because, also mark this really closely, the reason why we need this is because the chain rule essentially is suited for functions that are a function inside a function. So we see this to the power of 3 over 2. This is an exponential function, and there's a g of x, which is this one right here, that's another function inside it. We're just giving it variable names. And a great way to tell if we should use chain rule is usually in chain rule there's always brackets involved. Now, using the simple formula here, as we just right now distinguish our f and our g of x, we know that our f of x is the outward one, which is 3 of 2. So using the formula here, which is essentially our chain rule, notice how like we first have to decapitate the outing and then do the middle, kind of like a chain, or even like a banana, we do that. So we essentially use power rule for f because we need to find the derivative of f. And also, by the way, you don't need to use power rule. It honestly depends on what function you use. But essentially what I did was I used power rule for this and I put my function in. But looking at the formula, it looks like the g of x stays the same in the bracket and it replaces the x inside it. And then what happens is that we have to multiply it by the derivative from the outside. So that's what I did essentially. I can't use the chain rule for this function now, so that means my only way is power rule. And so essentially then, this is the exact answer. Now what you're going to notice, especially with using chain rule, is that none of your teachers in grade 12 will actually ask you to simplify because chain rule often involves complex exponents. So you can just leave your answer at this and it'll make fine. And this is the rate of change of your equation. Even solving much more harder and strategic problems like this, we still incorporate chain rule. The thing is, the reason why we even do is because there's a function inside a function. I'll give you guys a few minutes to think about what the function inside a function is. Okay, a few minutes go by. Great job, guys. It's right here. This is the function inside a function, and that's why we use chain rule. Yes, we have this too, but this doesn't affect this inside because this doesn't affect the bracket. It's not multiplying, it's not dividing, it's just subtracting it, meaning that there's not bed mass, essentially. We don't prioritize the subtraction as much. And therefore, that is the end of our lesson. So today we went over why chain rule is called chain rule, how it's derived, how to basically function it, and if you have any comments or concerns or questions, please come see me. And also, I just want to add in that the main reason why we even use chain rule and why it's so important is because it's basically used every single day. It's the reason we have vehicles and computers and such. Essentially what happens, even money, essentially what happens is that we know that derivatives are the building blocks of life because physics is based upon derivatives. Physics is based upon how quickly an object moves in motion. And chain rule is one of the most important formulas because there are so many situations out here with a function inside a function. For example, money, like revenue and interest and your rates and such. Chain rule covers how to find the rate of change for that. And therefore, it's important to have this knowledge because in the future, especially in higher level math, we're going to be seeing ways of more manipulation to the chain rule, which is essentially just a formula. So yeah, that is the end.